Op-amp internal circuits. Welcome to this module on the internal circuitry of op-amps from National Semiconductor. This module is 14 pages in length and lasts just over 20 minutes. Here is a very simple and general amplifier, and there are very many different variations to op-amps internal circuitry and design. The graphic is just showing the op-amp's standard triangle. Instead of having 3 blocks to represent different stages of its internal circuitry, we have inserted the actual schematic. This should help in the process of understanding what each transistor is supposed to achieve. The graphic is zoomed in on the circuit schematic without showing the pins. Here is the internal circuitry of the LM741, which is very basic configuration that you will see in operational amplifiers, and that includes an inverting and a non-inverting closed-loop configuration. The first part of the circuit is the biasing circuit of the amplifier. The biasing provides the device with the current that it needs for driving all of the transistors in it. For this particular design, the biasing branch consists of Q12, R5, and Q11. The current through R5 is equal to VCC minus VEE minus the 2 diode drops across Q12 and Q11 divided by the value of R5. This current is seen at the base of Q11. The next stage is the differential input stage of the amplifier. The current at the base of Q11 is mirrored to the base of Q10. This current is then delivered to the base of Q3 and Q4. The differential input stage consists of Q1 and Q2 in series with Q3 and Q4. Any differential signal across either one of these inputs will flow current through the input stage and then to Q8 and Q9. Q1 and Q2 are connected as emitter followers. This provides the high input impedance that in the input stage of this stage and eventually the operational amplifier needs. Q3 and Q4 provide DC level shifting. They also protect Q1 and Q2 from emitter-base junction breakdown. For NPN transistors, the emitter-base junction breakdown happens at about 7 volts of reverse bias. For PNP transistors, this breakdown happens at about 50 volts. If, accidentally, the input pins have a large reverse voltage across, Q3 and Q4 actually protect Q1 and Q2 and prevent the op-amp from breaking down. Q5, Q6, and Q7, along with the resistors R1, R2, and R3, form the load circuit on the input stage. This is a high impedance load, and this load converts the differential signal of the input transistors into a single-ended signal at Q6's collector. The single-ended signal is then delivered to the second stage of the amplifier, which is the gain stage. The signal from the collector at Q6 is fed into Q16's base. Q16 is connected as an emitter follower, which gives this stage very high input impedance. Since it minimizes the loading of the input stage of the amplifier, it prevents gain loss at this stage. Q17 is connected as a common emitter amplifier. The load of Q17 is the output resistance of Q13B and reaches the PNP transistor and parallels with the input resistance of Q23, which is another PNP transistor. Output of the second stage of the amplifier is taken as collectors of Q17. One concept that is repeatedly used in op-amp circuits is active load. Active load is when a transistor current source is used as a load resistance. This way you can achieve very high gains without the actual need for high resistors, and this helps us by saving chip area. Also, having a large value resistor would require a large supply voltage source. By using an active load, we no longer need to have the high supply voltage. An example of this active load is the load on the collector of Q17. A compensation capacitor is used in this part of the circuit. It is a Miller compensation capacitor, which provides frequency compensation for the amplifier. It is connected in the feedback path, and it creates a dominant pole at about 5 Hz. This is going to shift the other poles of the amplifier further out. It also gives the op-amp a fairly uniform 20 decibels per decade drop. Here is the output stage of an op-amp. Q14, or the source transistor, and Q20, or the sink transistor, form the output complementary stage of the amplifier. Q14 and Q20 have larger areas compared to the other transistors, so that they can provide larger currents with minimal temperature effect on the device. When the output of the amplifier is pulled positive, Q14 conducts more power and it pulls the output more towards the positive supply. The opposite happens when the output is pulled negative, meaning Q20 is going to conduct more and the output is actually pulled more towards the negative supply, and it will move downward. This amplifier has short-circuit protection. Not all amplifiers have short-circuit protection. Q15 provides short-circuit protection for the source transistor, or Q14 and Q21 provides short-circuit protection for the sink transistor, or Q20. Also in this output stage, we see that Q18 and Q19 bias the output transistors in the linear region, and these two transistors are fed by Q13A, which is shown at the very top of the circuit. Q23 is connected as an emitter-follower. This minimizes the loading effect on the output of the second stage of the amplifier. The output stage that we've presented here is a Class AB output stage. As we've already mentioned, Q14 and Q20 have larger areas. That's because we want to be able to draw more current from them. The output of the amplifier has very low output impedance.